To the continuation in our deep learning series. Uh, Today we shall be looking at the cost function. Remember, the cost function is the same thing as the objective function, which is also the same thing as the loss function. And all we're trying to do is we're trying to measure how far away is our predictions from the actual values. Remember, for in order for us to be able to um, adjust our weight parameters, we need to measure what's different between our actual values and the predictions, so that we can adjust our weight parameters in such a manner that the difference between the actual and predictions will be minimized. That is, we're trying to actually minimize the total error. Now, how do we choose our parameters W? Remember that when we calculate the total error, which is this E of W, for linear regression, this is the formula for calculating uh, the total error in linear regression. In logistic regression, we introduce the notion of what is called the sigmoid function. That is, we actually pass the result, we actually pass our function through the logistic function, the sigmoid function. You remember here, we actually squash our z into a logistic function, so that we can learn a linear decision boundary between the categories. Here, the intuition behind our cost function is we want it in such a way that if y equals to 1, our prediction should also be equals to 1. But if otherwise, that is, if we miss the target, if we actually miss the prediction, then there should be some penalty for that. As you can see in this course, in this plot, y is 1 in this plot, so we expect our h of w to also be equals to 1. So if our h of w equals to 1, then our cost function will be close to near 0. But if our h of w is tending towards this way and is getting close to 0, then we are going to have a high cost function. That is, we are trying to penalize our algorithm that this uh, value of h of w is not supposed to be. So, and this negative log h w achieves this course. It achieves this plot, this curve that we see. For us, the plot of negative log gives us this, and that is why we have the cost function for our logistic regression to be negative log hw if y equals to 1. This corresponds to this. Now, if y is equals to 0, we make use of this cost function, which gives us this plot. That is, if the actual value is y, the actual target is 0, we expect that h of w to also give us 0 or something near to 0, which means that the value of our cost will also be minimal, will be very close to 0. But if h of w gives us something that is large, that is getting close to 1, then the cost function will also be high. That is to penalize for that, for the fact that our model is missing the actual target, and that corresponds to what you have here. So this curve, negative log 1 minus hws, corresponds to this curve that satisfies our intuition. Now, what do we want to do? In order to fit our parameters, we want to minimize our weight matrices, our W. That's essentially what we want to do. And in logistic regression, whatever it is that our h of W gives, we want to compare the value with a threshold. In this case, our threshold is 0.5. And we're saying if it is less than or equals to 0.5, then it will belong to categorized as 0, and otherwise it will be categorized as 1. Okay, so essentially what is happening in this place here, we have replaced the cost h w, this we have replaced it with the whole of this that we actually define here, negative log hwx and negative log 1 minus this, based on whatever it is and that our prediction gives. So this has been replaced with this. So in order for us to do gradient descent, we remember that gradient descent allows us to be able to uh, adjust our weight matrices such that we get the minimal error, we get the minimum total error. So, and what we do, this is our gradient descent algorithm. We continuously differentiate with respect to the weight matrix parameters, and we simultaneously update all the weight parameters, just like we saw for the linear regression case. So the algorithm is just uh, exactly the same as the linear regression, except that the only difference is in our own case we have introduced the sigmoid function to be able to squash our predictions between 0 and 1. So, logistic regression in a neural network. You remember that in a multivariate linear regression, we have seen this when we have more than multiple variables. Now, we also saw this, that what you do is you take the weight matrices multiplied by x, where this x here represents all this x, and where this w here represents all this w. In other words, the large W is actually equals to what you have here, the W0, W1, W2, up to we get to Wn. So this is a vector. And this x, as you guess, beta is supposed to be capital X. It is x0, x1, x2, then we'll move on until we get to xn. That is our capital X. Now, the difference with our logistic regression is we are now introducing this particular function, the sigmoid function. So whatever we have computed here, we pass it through the sigmoid function, which squashes it in between 0 and 1. Don't forget that what our sigmoid function does is this: it takes in a z, which in this case our z is w transpose x, and what it does is it evaluates 1 over 1 plus exponential of negative z. So that is the forward propagation. Forward propagation simply means we are starting from our input, which is x, and we are calculating this wt of x as we've seen before. We can just store that in a variable z. And what you do is that we are now passing our z into a sigmoid function to give us our predictions, and this is our prediction. Then we are now calculating the loss function. That is, we are calculating the difference between the predicted value and the actual value, and that gives us our error. In our backward propagation, the backward propagation is actually where we do the partial derivative to be able to optimize our weight matrices. That is, we're trying to adjust the numbers such that our error will be minimized. So in backward propagation, we start from the loss that we have calculated, and we do a partial derivative of the total error with respect to all of the weight matrices, and we adjust our weights simultaneously based on that total error, based on the partial derivatives. Remember, alpha is our learning rate. So the gradient descent in a neural network terminology, how is this done? This is an iterative process. what do we start with? We first of all do a random initialization of our weights and biases. Don't forget that this random initialization is actually taking some numbers and randomly giving them values. Most times non-zeros. We don't use all zeros. We give it some initial values, initial numbers for the weights and the biases. Then we push that into our forward propagation to be able to calculate the forward prop and pass it through the sigmoid function. Then we calculate our loss against our target values. Then once we get our loss, then we do the partial derivative, and that is the backward propagation process to be able to update our weight parameters. When we say update our parameters, we're actually adjusting the numbers based on the values that we have calculated through the partial derivative on each of the weight matrices. Then we go back again and do forward propagation again and measure how far away is our result on the loss. Once we've done that, we do a partial derivative again to be able to adjust the weight parameters, and the partial derivative is done based on each of the weight parameters that are involved. Then we update our parameters again simultaneously. We do the forward propagation again, and we'll continue this cycle from the first forward propagation back to the forward propagation to backward propagation. This make up a complete cycle, and that is one iteration. Then we go again forward prop, backward prop, make up another iteration. That is second one. We go again, this make up the third iteration. So we continue this for a number of predefined iterations until when we say convergence. Then when we are done, we can exit the loop and make our final prediction. So, thank you for listening. Next time we shall continue with neural networks proper.